power, energy. This topic is actually very beautiful. It is, uh, I can say, a better version of Newton's laws. Actually, we modify Newton's laws to define terms like work done by a force or kinetic energy or potential energy and things like that. If you see force and of course force causes acceleration, these are vector quantities. So dealing with them is a bit tough, vector quantities. But sometimes, we have better methods than dealing with these vector quantities. From force, we define what is called work done by a force, which is of course a scalar quantity. And corresponding to acceleration, we define kinetic energy and so on. So these are scalar quantities. And dealing with scalar quantities is easy. Dealing with these is easy because you can directly add them and so on. If you want to add forces, we have to use some triangle law, parallelogram law, or if you want to do something with accelerations, again you have to do the vector analysis. You have to add accelerations, you have to add them using parallelogram or triangle law, or there may be some cross and dot products dealing with vectors and so on. But when you come to a scalar, it's much easier to deal with. So what we are doing in this chapter is we will define scalar quantities from these vector quantities. So from force, we will define work done by a force. From acceleration, we are going to define kinetic energy, so that we can solve the same problems of Newton's laws using work energy. That is our motto. So that is our motto. So let's see. Our first definition would be work done by a force. Work done by a force. ఈ తలుపేసేమో సత్య ఈ తలుపేసేవా. So work done by a force. Let's define it. Most general definition. Most general definition is work done by a force is defined as integral F dot ds. So you see this definition, integral F dot ds. This is how we define, use the most general definition. I am first introducing you to the most general definition. Then we will go to the specifics of this. So we should never forget the most general definition. That is most important. So why we are defining it like this? So let us understand. First of all, you might be applying this force on some object. So there may be some object on which you are applying this force, and you want to find work done by this force. But not only this force, there may be many other forces acting. There may be some F1, there may be some F2, and so on. But I am not really interested in work done by them. I want to find work done by this force. I want to find work done by this force. There may be many forces acting on the object, but I just want to find work done by this force. And under the action of these forces, let us say the body moved in such a path. Now, what we are doing is we are dividing this path into little displacements. Let's say this displacement is ds1, the next displacement is ds2, next displacement is ds3, ds4, ds5. Like this, I am dividing it into infinitesimal displacements. Okay, infinitesimal means tending to zero. And how many such displacements are there? There are infinite number of them. So I have divided it into small displacements. Why I am doing like this? Because this force whose work I am trying to calculate, this force, whose work I am trying to calculate, it may not be constant. As the body is moving, this force could change value and this force also could change direction. So what I am doing is, for every small displacement, I take the value and direction of that force. Let us say initially it was F1. Don't confuse with this F1. I'll call this as some F dash, F double dash I'll call this to avoid any confusion. So our force F, for some time it had a value and direction F1, and I am taking dot product with ds1. This will give me the work done by the force for the small displacement. So I am doing a dot product of force and displacement, but not a big displacement, but a very small displacement, because the force is changing from movement to movement. The next moment the force became F2 and I dot it with the next displacement. Uh, and in this way, just 1 minute. Yeah. And next, for next displacement ds3, the force is F3. And this way I find force for every small displacement. I find work done for every small displacement. And I add all these work done. Now there are infinite displacements here. So adding them would take the form of an integral. So the definition is work done by a force. General definition is integral f dot ds. Why I am doing dot product with ds? What is the reason? Now that I cannot justify it, because if we do that, we get a quantity and I am calling that as work done by the force. So I am defining a new quantity where you take the force, and for a small displacement, if the force does not change, you take dot product of the force with that small displacement, and the quantity you get is work done for that small displacement. I am defining it like this. Will it be of some use to me if I define it like this? Yes, it will be fantastic, because certain class of problems will be solved very easily using this idea. Now, so when you add all of them like this, there are infinite number of displacements, because you have divided this whole big curve into displacements, each of which is tending to zero. Each of them is tending to zero, and there are infinite number of them. So you are adding kind of infinite terms, and that takes the form of integral. So most general definition is integral f dot ds. Now note, along with this force, there are many other forces. So the body is moving under the action of all the forces, but I am finding work done by my specific force. So I do integral f dot ds. If you want work done by f dash, this force, do integral f dash dot ds. If you want work done by f double dash, do integral f double dot ds, f double dash dot ds. So this way, whatever is the force, we can find work done by that force. So this is the most general definition. So whenever you want to find work done by a force, if you don't know anything about that force, you have to use the most general definition. So this is most important. Now let us come to some special cases. Special cases. There is also one more thing here I want to tell you. What is this ds? Now look at this. ds is, now to be more precise, it is displacement of that point where force is applied, or some people call it displacement of point of application of force. Why I should write like that only? Because sometimes, suppose you take a bubble gum, there may be a bubble gum, a chewing gum, and suppose you applied a force here. The whole chewing gum may not move, it may be at rest only, but this part may deform. It might become something like this. It may deform. So this point went there. Okay. Now, should we say whether this F did work or not? Yes, it did work. Even though the whole body did not move, the point where force was applied, that point, that underwent a displacement. So this has done work. So if the total displacement is S, again I will chop it into ds1, ds2, ds3, ds4, and I'll do f dot ds and integrate. So here what is ds? ds is displacement of uh, that point where force is applied. Okay, it may not be displacement of whole body. Whole body may not move. When you push a chewing gum, for example, suppose it has been stuck to a wall, the chewing gum, and you are pushing it, it won't move. Only that section where you are pushing it might deform. So to find work done by your force, you must take only displacement of that section where you are applying force and do dot product and integrate. So that is what you have to do. So in the general definition, the most important thing is when you write work done by a force F as integral F dot ds, ds is displacement of that point where force is applied. This is the most important thing. Now, having said this much, now let's go to the special cases. What are the special cases? So, special case 1, force is constant. This is one of the most common cases which we encounter. So, when I say force is constant, neither its magnitude nor its direction should change. Both are not changing. Magnitude should not change, direction also should not change. If any one of these changes, then the force is not constant. So, if force is constant, then can we simplify this definition of work done by the force integral F dot ds to something else? Let us see that. We can pull F out of the integral because it's a constant, including the dot product, and write it like this. Now, how did you write like that? If you go ahead, okay, and go to the fundamental definition of integral. So we wrote integral F dot ds actually as F1 dot ds1 plus F2 dot ds2, so on, like this. Now I am really saying that this force F is constant. So F1, F2, F3 all are same, their magnitude and direction, because it's the same force which is acting. So I can write F dot ds1 plus F dot ds2, because the force is constant. It's not changing in magnitude or direction, like this. You can take F dot common and you can write ds1 plus ds2, so on. If you look at this, is nothing but you are adding all little displacements, infinitesimal displacements. So there is integration of ds. That's how I wrote this. Now when you add ds, when you add all these little ds, what do you get? You get the net displacement. How? Look, suppose the particle went in this path, you take all these small displacements, ds1, ds2, ds3, ds4, ds100, ds1000, ds1 million, so many displacements are there. They are all put head to tail. If you see, at the head of first displacement there is tail of second displacement, at the head of second displacement there is tail of third displacement, and so on. So when you add all these by Polygon law, it will be this this vector from the initial tail, the tail of first vector, to head of last vector. So this is nothing but the net displacement of that particle or the body, or net displacement of that point where force is applied. Like chewing gum example, net displacement of that point where force is applied. So I can write it as F dot S net. When can you write like this? Only when force is constant. So this is a very powerful idea, because most of the time we encounter constant forces. So work done by a constant force is F dot S. So this is not a general definition. It works only for constant force. The general definition is of course integral F dot ds, where ds is displacement of that point where force is applied. Okay. So work done by, let me write here, work done by a constant force F is given by F dot S net, force dot product with net displacement. This is a very useful idea. Sometimes, when you expand this dot product, You get F into S net into cos of angle between them. In some applications, if you combine F and cos theta, it might look simpler. You can do either way. In some applications, if you club S net and cos theta, it might look simpler. For example, if you say F cos theta into S net, it actually means force along displacement, component of force along displacement multiplied by displacement. That is the meaning of this. F cos theta is force along displacement multiplied by S net, which is the displacement. Or you can do like this, force into displacement along force. S net cos theta is displacement along force. I will show you one example where we can use this idea. So first you should understand that work done by any force is integral F dot ds. Work done by constant force is F dot S, where S is the net displacement. That F dot S we can write it as Fs cos theta. You can club cos theta with F also. It's up to you, or you can club cos theta with S net also. Let's see one example. Suppose I have an inclined plane and here I have kept a block of mass m. I'm just trying to adjust it so that it looks a bit better. Okay, so I have a block of mass m, and suppose this block came down till here. Okay, so this is the net displacement of block. Now this height, let us say, is h from where the block was released. I am interested in, there is of course gravitational force mg acting, so I am interested in work done by the gravitational force mg. Now we are not dealing with cases where you are releasing the body from deep outer space and it is coming towards earth, or some asteroid coming towards earth. No, we are releasing this block on an inclined plane which is on earth only. So in that case we can take the force due to earth as constant, okay, both in magnitude and direction. So whenever you are close to surface of the earth, the force is more or less constant. If you go deep into outer space, then the earth force will decrease as you go away. The earth force will decrease as you go away. I am not doing that. I am only looking at on the very small area on the earth. So there this force is a constant force mg. Its magnitude is also constant, direction is also constant. If you go to North Pole and there is a ball here, its force is mg. If you take it at equator, its force is mg. Direction has changed at least. Even g value slightly changes. But I am not doing that here. The block is coming in our room from certain height, and in our room the gravitational force is more or less constant. So mg is a constant force. So how to find work done by mg? You have to take dot product of mg and the displacement. Okay, mg is down, shown in the blue color, and displacement is shown in the yellow color. So you can write mg into the displacement into cos of angle between them. But I want to show you a better method. If you see, work done by constant force is displacement multiplied by force along displacement. You can do that. That's one way. Now this angle is 90 minus theta. So displacement is S net. Force along displacement is mg cos 90 minus theta. That is mg sin theta. And S sin theta is actually h only. You see, S net is hypotenuse. Hypotenuse into sin theta is opposite side. So you are getting mgh as work done by gravity if you do like this. This is a slightly longer route. What is the other way? What did I do here? F dot S only I did. Why I did F dot S? Because F is a constant force, mg in this case. and I am doing dot product with displacement. So you must take the force, you must take the displacement and multiply by cos of angle between them. That is dot product. So mg into s net into cos of 90 minus theta, which is mg s net sine theta. That, but s net sine theta is h, so I wrote mgh. The other way is you can write displacement along force multiplied by force. This is a more easier method. Here I did force along displacement multiplied by displacement. Now I am doing displacement along force multiplied by force. Force is mg. What is displacement along force? You see here, the total displacement was this, which I can split it into vertical displacement and horizontal displacement like that. In that one displacement, the horizontal is perpendicular to force. What is the displacement along force? It is vertical displacement. This displacement is perpendicular to mg. I don't take that. I only take displacement along the force, right? Displacement along force is h. So I directly get mgh here without doing anything. Displacement along force is h. Displacement perpendicular to force is something, this, that. Okay. So I get it, the same answer I am getting, but much easily here. So you have a choice. When you are finding work done by a constant force, it is F dot S. You have a choice now. You can write it as Fs cos theta, no doubt. But you can club that cos theta with F and say it is component of force along displacement. For example, mg cos 90 minus theta. That gave me mg sin theta here. That is force along displacement multiplied by displacement. Or you can do the other way. Displacement along force. That is already h. Displacement along force. Displacement in the direction of mg. That is h. Multiply by mg. That is mgh. So force along displacement multiplied by displacement, or displacement along force multiplied by force. Either way, you get same answer. But sometimes one method may be faster. I like this idea of displacement along force multiplied by force. This idea I like very much. Is faster sometimes. So that is work done by constant force. So that was special case one. So work done by general force is integral F dot ds. Work done by constant force is F dot S net. That is one case. There is another case where the force may be variable. Force may be variable, but it is always, look at this word, always perpendicular to the infinitesimal displacement. Every moment the force is perpendicular to ds. So if the body was going like this, here the displacement was like this, and the force whose work you are calculating is maybe like this, perpendicular. Next moment displacement is like this, the force perpendicular to displacement may be like this. Force is a variable force only, but it is always perpendicular displacement. Next moment the displacement may be like this, the force may be like this, but it is always perpendicular to displacement. Next moment the displacement is like this, the force may be like this, perpendicular to displacement. So even though the force is variable, but whenever you look at it, the force is perpendicular to that ds. In such a case, if you write integral f dot ds, at every moment f and ds are perpendicular, so the dot product will be 0 and total work done by such a force will be 0. So if the force is perpendicular to displacement at every moment, not at one moment, at every moment, then work done by such a force is 0. Best example would be if you take uniform circular motion, body is moving like this with a velocity v, so the displacement v dt will be in that direction along velocity ds. ds by dt is v na, so I wrote ds, that small displacement, as v dt. It will be in the direction of v, so in this direction. But what about the force in uniform circular motion? It is towards center. We call it centripetal force because it is pointing towards center. It may be some gravity, some friction, whatever, depending on the case. So the force and this ds, which I shown with blue color, which is along velocity, both are perpendicular right now. What about next movement? Suppose you take here. Again, force is towards center because it is centripetal. Displacement is along tangent. Again, they are perpendicular. Whenever you look at it, force and displacement, force and displacement are always perpendicular. So in this case, work done by that centripetal force, whatever it is in that case, on this object moving in circular path is zero. That is second special case. So integral f dot ds, if f perpendicular to ds, not at one moment, not at one moment, always, always, this is a very important point, then work done by such a force will be zero. Example, any force which is acting towards center in circular path. Example, any force, because it is pointing towards center, we call it centripetal, but you should tell what is that force. Is it gravity, friction, whatever? Any force that acts towards center in circular path does zero work. It doesn't do work because every moment force is perpendicular to displacement ds. Every moment that small work done will be zero. If you add all such work done, totally you will get zero. So that is special case 2. So I have got general case where integral f dot ds is work done by the force. If force is constant, f dot s net will be work done by the force. That is one special case. If f is perpendicular to ds at every moment, then f dot ds will be 0 and integral f dot ds will be 0. That is another special case. So I have general case, I am writing here for clarity, work done by the force is integral f dot ds. Special case 1, where force is constant, in that case the same definition will become f dot s net, that will be work done by the force. Special case 2, just one second. Okay, special case 2, this is when f is perpendicular to ds at every moment, then f dot ds will be 0 at every moment. Little work done are 0, so total work done is also 0. These are the three main cases which are very important for us. Now what we will do, we will take one example where all three cases are going to come. Just give me 1 minute. So all three cases are going to come, and that is a very beautiful problem. It's a problem from the old classic textbook Resnick and Halliday. Very beautiful book. Nobody is using nowadays. Very beautiful book. So there is a small object tied by a massless string of length L. So string is, let us say, string is massless because that's how we have been taking in Newton's laws most of the time. Pulleys and strings are massless. Even in work energy, most of the time we take the pulleys and strings to be massless. This is a small object of mass m, and I am applying a horizontal force on it. So F is horizontal force. I am not saying it's a constant force. I'm only saying it's a horizontal force. And the ball or the object is slowly pulled aside till string makes theta with vertical. Okay, till string makes theta with vertical. Find A, work done by tension, B, work done by mg, C, work done by F in this process. F is a horizontal force, but you can adjust its value. It is a variable force, and How are you taking the ball to the side? Slowly. Now we'll understand what is meant by slowly here. But he is asking work done by tension acting on the ball, work done by mg, and work done by F. This is what he's asking. So let us step by step solve it. First, we will find work done by tension. Before that, let us understand what is meant by the word slowly. How do you uh, understand slowly in the context of physics? See, whenever this word slowly comes in physics, it means, I'm just giving a example, but exactly this is how it is. The ball moves 1 millimeter in 1 million years. That is the meaning of slow. Let me explain. The ball is moving 1 millimeter in 1 million years. So the speed of the ball is 1 millimeter per million years. Million years is a huge span, right? We don't live that many years. 70, 80, 100 maximum. 100 years we might live by God's grace. If we have good grace, 100 years. I'm saying million years. In million years, it moves by 1 millimeter. So in 100 years, which is a very small time, you might not even see the ball moving. It's like the ball is moving slowly means it's almost not moving for you, which means the net force on the ball is zero at every moment. The net force on the ball is zero every moment. That's the meaning. Okay. So if I take some intermediate position, let me take some intermediate position where this ball is making an angle phi. Okay. Ultimately, it's making an angle theta. That is in the final stage. But I'm taking some intermediate position where ball makes angle phi with vertical. What are the forces acting on the ball? There is a tension acting like this. There is mg, and there is your applied force, and the ball is moving in such a slow way that you don't see it moving. That means it is in equilibrium. Acceleration is zero. When we don't see something moving, we say it is at rest. Net force is zero. So if I balance vertical forces, you must have T cos phi equal to mg. So I'm taking component of tension in vertical direction, T cos phi. F doesn't have any component in vertical because F is horizontal. Then in the horizontal, I can say T sin phi equal to F. This is vertical equilibrium. This is horizontal equilibrium. Totally, the ball is in equilibrium. From here, if I divide, I get tan phi is F by mg, or F equal to mg tan phi. So I got some idea about my applied force. Okay, my applied force with which I am pulling this ball slowly is such that as phi increases, my applied force also should increase, because when you increase the angle with vertical, the ball has a tendency to come back. So you must apply greater force. As you start pulling it more and more, you have to hold it with more and more greater force so that it doesn't come back, because you are applying horizontal force. Understand that you are not applying a tangential force. Maybe if you are applying something like this, I don't know, but you are applying horizontal force. So as it goes side, you will apply more and more so that it doesn't come back. So the force F is a variable force. So this is a variable force. So I have now three forces with me. Tension. I don't know whether tension is constant or variable. My take is it is variable because it depends on F also. Then mg is a constant force and F is a variable force. All three are keeping the ball in equilibrium at every moment. Now we have to find work done by each of these by the time the angle becomes theta. That's what he's asking. Find work done by tension, find work done by mg, and work done by F. Now, if you see, the path of the ball is a circle with this thread as the radius. Okay, the thread is inextensible. So the distance of the ball from this center is always L only. So it has to go in a circular path if it's going in a plane circle. Okay, which means the tension is this is pointing towards center of circle. So it's a force which is centripetal in this case, pointing towards center. There is also a part of mg which is centripetal, and f also is centripetal, but I am not interested in them right now. I am interested in tension. Tension is centripetal force. Okay, it is pointing towards center in this case. Any force that points towards center is called centripetal. You should be able to tell what is that force. In our case, it is tension. And at every moment, the displacement ds is perpendicular to tension. So work done by tension has to be zero. This goes into our second special case, right? The second special case is when F is perpendicular to ds at every moment, then work done by such a force is zero. That is what is the idea behind tension here. Next, we have to find work done by mg, which is a constant force. That goes into special case 1. So I have all the cases here. I have a variable force which is F, which changes with angle, variable force. Then I have a centripetal force which is tension. Then I have mg which is a constant force. So all are there in this example. That's the beauty of this example. So it is kind of making all that we have learned right now clear. It's making very clear all those ideas. So how to get work done by mg? Now look here. This ball started from this position and finally it came up to an angle theta, and this length is L. So if you drop a perpendicular here, till here it will be L cos theta by trigonometry, but total string length is L, so this will be L minus L cos theta. So essentially the ball went up by height L minus L cos theta. Okay, so you see mg is acting down. The ball actually has a displacement like this, which I can split it into horizontal, horizontal and vertical. Okay, this is the net displacement of the ball, which I can split into SH and SV. Now mg is a constant force, so work done by mg I can use F dot S net, right? F dot S net, constant force, we can use F dot S. Variable force, you have to use integral F dot ds. What is ds? The displacement of that point where force is applied. Okay, now I can say mg is the force, g is acting down. I dot it with net displacement, which I can write as SH plus SV. mg is vertically down, whereas SH is horizontal. So this dot product will become 0 because mg is down and SH is a horizontal displacement. Their dot will become 0. Whereas the other dot, this one, mg is down and SV is up. So the angle between them is pi or 180 degree. So their dot product will be giving me magnitude of force into magnitude of SV into cos of 180, which is minus 1, minus mg SV. What is SV? L into 1 minus cos theta. You see here, minus mg L into 1 minus cos theta. This is work done by gravity. I used F dot S and I split S for convenience into horizontal and vertical. Horizontal displacement doesn't yield any work because mg is perpendicular to it. Vertical displacement will give some negative work done by mg. Negative work because mg is pulling down but ball is going up. Okay, so mg is doing negative work. So tension did 0 work, mg is doing a negative work. And now I am left with work done by F, which is a variable force. So let's calculate that. How do we calculate it? Look, force is changing. When things are changing, you have to integrate, no choice. So you have to use integral F dot ds. How are you going to use it? You must find the force. Whenever you are integrating, you must find that quantity, whichever you are integrating, at some intermediate position, not in the initial or final, intermediate position. So what is the intermediate position? When the angle is phi. When angle was 0, that was initial position. When angle is theta, which is mentioned in the question, that is the final position of the string. So initially the string was like this, making 0 angle with vertical. Finally the string is something like this, making theta angle with vertical. I'm taking some intermediate situation where it is making phi with vertical. That's the idea. So we must take some intermediate position. So in the intermediate position, the ball is making angle phi with vertical. you are applying a horizontal force and tension is there, and of course mg is there. We found work done by tension, work done by mg already. Now, so the force right now we already calculated at that position, it is mg tan phi. We saw this by putting horizontal and vertical equilibrium. The critical point is the ball is moving very slowly. That is the very critical point given in the problem. So if it is moving very slowly, acceleration is zero. So vertical force is balanced, horizontal force is balanced. From there we got F as mg tan phi. So the force at intermediate position is mg tan phi. Okay, in which direction it is? Horizontal direction, mg tan phi. And what about the displacement? Force, and I must dot it with the ds, integral f dot ds, right? What about displacement? Displacement is tangential, it is in this direction, tangential, perpendicular to radius, tangential. Look very carefully. If this is phi, this angle is 90. So this angle will be 90 minus phi. Okay, 90 minus phi. Then what about let me use a different color. What about this angle? That angle will be phi. Why? Because you see total is 180 straight line. In that this 90 is gone, perpendicular, radius and tangent. So if this is 90 minus phi, this should be phi. So I have like this, total is 180. Okay, this is 90 minus phi, this is 90, this should be phi. So the total is 180. Okay, total is 180. So this is my displacement, which I can say it further covered an extra angle d phi. So at some intermediate position, the string was making angle phi, and in a small time it further increased that angle by d phi. Why I am doing like that? In calculus, after x you must bring dx into picture, after y you must bring dy into picture, after phi, which is an arbitrary angle covered by the ball, you must bring d phi into picture. Okay, the variable and d of that variable both must come into picture. So if that angle is d phi, what is this line? You can say it's a small arc also. Arc length will be radius, which is length of the string, into angle d phi. That will be this. So force is mg tan phi, displacement is L d phi, angle between them is phi. Can you see that? Displacement is a straight line. Why is it L d phi? Actually, arc length is L d phi. If it goes in an arc like this with the d phi angle, arc length is L d phi. But if d phi is very small, this arc length is straight line only, because d phi is tending to 0. So that displacement is L d phi. So I got the variable force, I got the displacement, I got the angle between them. So we should use f ds cos theta. F is mg tan phi, ds is L d phi, cos theta is cos phi. F ds cos theta you use, or f dot ds, integral, with phi going from 0 to theta. These are the limits. Initial angle, final angle you will give as limits. Phi was some intermediate angle. So if you do like this, mgl is a constant. Tan phi into cos phi is sin phi. Sin phi integral is minus cos phi, and you have to put limits 0 to theta. So minus mgl cos theta minus cos 0 is 1. So if you absorb the minus sign, it will be plus mgl into 1 minus cos theta. So work done by this variable force is plus mgl into 1 minus cos theta. Work done by mg is minus mgl into 1 minus cos theta. We already did that. Work done by tension is 0. In fact, if you see work done by all forces acting on the ball, there are only 3 forces: F, mg, tension. If you add all of them, plus mgl 1 minus cos theta minus mgl 1 minus cos theta, 0. All 3 when you add, it becomes 0. Work done by all forces is 0. Why? We will see soon that work done by all forces should be change in kinetic energy. And kinetic energy is not changing because the ball is going very slowly. So definitely work done by all forces must be zero. So I told you about work done by variable force, integral F dot ds. ds is displacement of that point where force is applied. I told you work done by constant force, F dot s. You can write it as Fs cos theta, or you can say force into displacement along force, or you can say displacement into force along displacement. Third case is if F is perpendicular to ds at every moment, then work done by such a force is zero. It should be perpendicular to ds always, not at one instant. Every instant, if force is perpendicular to ds, work done by such a force is zero. This is what we have to begin with. Now, we are going to discuss about a special class of forces, called conservative forces. Among forces, we are going to discuss this special class of forces called conservative forces. What is a conservative force? We should understand this. Very important for us. What is a conservative force? The answer is, if work done by a force in any closed path is zero. Whichever closed path you take, in that it should be zero. Or it is better if I say work done by a force in all the closed paths is zero. That looks much better. In all closed paths, whichever closed path you take, then it's conservative. That is the meaning of conservative force. The force should be such that work done by it in all closed paths, whichever closed path you take. It's up to you. It should be zero. It may do work. In some part, it may do positive work. In other part, it may do negative work. But by the time you complete and come back to the starting point in a closed path, it should do zero work. That is one definition of a conservative force. One definition. The other definition, uh, which you can prove from this first one, first and second are interprovable from each other, is if work done is path independent. If work done by a force is path independent, then it's a conservative force. These two statements, 1 and 2, are interconvertible. I'll prove it in a minute. But there is a third one. It can also be derived from this first and second, but it requires uh, a calculus which is beyond our scope. It requires some vector calculus. There are some powerful theorems like Gauss theorem and Stokes theorem. It requires that. So a force is conservative. A force F, this is a very useful definition for us. A force F is conservative if del cross F is zero. What the hell is del? I'll introduce you to del in a minute. It's a vector operator. It's not a vector. It's a vector operator, and it is given by I dou by dou x. What is dou by dou x? It's a partial derivative plus j dou by dou y, not complete derivative. I'll explain what a partial derivative is also. K dou by dou z. This is the operator. What goes in the brackets? Well, I don't know what goes in the bracket. That's why I'm calling it operator. For example, if I write d by dx, that's an operator. We saw this in our calculus lectures very deeply. It's an operator. It expects something containing x and transforms it to give some value. For example, if I give it x square, it gives me 2x. So d by dx is an operator. X square is the operand, the function. Okay, but this is a complete derivative. But here I'm using partial derivative, dou by dou x. I'll explain what it is. But it's not just a normal operator, differential operator. It's a vector operator. I, j, k are coming into picture. That is what is del. So first, let me explain you what is a partial derivative. Then we will go to this del. and what all we can do with del, I'll tell you that. But the most important thing for us is a force is conservative if del cross f is 0. How to do del cross f? What is del cross f? I'll come to that. So first let's go to partial derivative. Okay. I know that d by dx of, suppose it is a complete derivative. Suppose I have xz. Then what we are doing, x dz by dx, we are using product rule plus z dx by dx. First I kept x as it is, differentiated z. Then next step I kept z as it is and differentiated x. This is the complete derivative. But when I say partial derivative, okay, then what I do is, whatever is the variable, only that one will be the variable. Everything else will be treated as constant. So when you use partial derivative, z is no more a variable, it's a constant. So I take it out and I differentiate only x, so it will be z. What about the first case full derivative? X dz by dx plus z dx by dx is 1. In partial derivative, you got only this z. Dz by dx was 0 because in partial derivative, we take z as a constant. So in partial derivative, if I have dou by dou y, only y is the variable. Everything else is a constant. If I have dou by dou z, only z is the variable. Everything else is constant. If I have dou by dou x, only x is the variable. Everything else is constant. That's the idea behind partial derivatives. So to give you some more concrete examples, okay, to give you some more concrete example, let me come back here. Suppose if I gave you d by dx of x, y, z, is a very interesting thing. So you have to write it as, how to do three variable derivatives. First, keep xy constant, differentiate z. Keep xz constant, differentiate y. Keep yz constant, differentiate x. This is how you do it. Every time you are differentiating only one, others are kept constants. How did you get this? Well, you can first consider xy as one term, z as another term, and apply product rule. Keep xy as it is, take derivative of z. Keep z as it is, take derivative of xy. But you can further expand this, right? So this term will become z into, keep x as it is, take derivative of y. Keep y as it is, take derivative of x. So if you see, that's exactly what you got here. It's a complete derivative. But if I write dou by dou x of xyz, then only x is to be treated as variable. Y and z are constants, they come out. Any other variable other than whatever is in the operator, that's a constant if you are doing partial derivative. So you do dou x by dou x. Dou x by dou x is 1, so it gives yz. For example, if I have dou by dou y of zx, this should be 0 because except y, everything else is a constant and you are taking derivative of a constant, damn it, so it has to be 0. Okay, so that's regarding partial derivative. Now coming back to the del operator itself, it's a vector operator. I am calling it as an operator because on what it is operating is right now not clear. Okay, so I just wrote del as I dou by dou x plus j dou by dou y plus k dou by dou z. On what it is operating, I don't know. There are three ways in which you can use this del operator. You can use del on a scalar. Let us say, for example, temperature. Suppose temperature is dependent on xyz coordinates. Temperature as a function of xyz, let us say, is x square yz. What does that mean? If you go to a room where coordinate system is put, if you go to origin in the room 0 0 0, their temperature is 0. If you go to 1 1 1 point, their temperature is 1 square into 1 into 1, 1 degree centigrade or Kelvin, depending on what unit you have. If you go to 1 2 3, what is the temperature there? 1 square into 2 into 3, 6 degrees centigrade. So point to point temperature is changing. Then how to find del T? I dou by dou x of x square yz plus j dou by dou y of x square yz plus k dou by dou z of x square yz, and that gives me I 2x yz. Why 2x yz? Y and z are to be treated as constants. You are differentiating only x square. Then in the next case, dou by dou y means only y is constant. So j x square z plus k x square y. This is what you got. So you got del of temperature. Del T is also called, if you apply del on a scalar, it's called gradient. So here we have done gradient of temperature. What does this tell you? It tells you the direction in which you have to move so that temperature is changing quickly. For example, suppose you are at 1 comma 2 comma 3. You are at this point. What is the temperature there? Put it here. 1 square into 2 into 3, that is 6 degrees centigrade. So you are at 1 comma 2 comma 3. Now you ask me a question, sir, in which direction should I move so that the temperature changes very fast? I want maximum change in temperature. You are at 1 comma 2 comma 3 in a 3D. In a 3D. So in which direction you have to move so that temperature change is maximum? So the answer is you find del T and put the point where you are staying. So if you put x1, y2, z3, I into 12 plus j into x1, z3, 3 plus k into x1, y2. You move in this direction right now. In that direction, you are right now at 1, 2, 3. Try to move in this direction and you will find maximum change in temperature. But the moment you move, now you have a new coordinate. Now from there, how you should move? Again, put it that coordinate here and it will tell you in which direction you have to move. Ultimately, you are getting a vector, right? Vector has some direction. 12y plus 3j plus 2k. You must move in that direction right now when you are at 1, 2, 3 so that the temperature changes by huge amount. So del T is giving you that direction in which T's change is maximum. For example, you can apply del on another scalar, like for example energy. Del of energy gives you that vector. If you move in that direction, the change in energy will be maximum. This is one way in which you can apply del. Del can be applied on a scalar. It's called gradient of temperature or del of. So del T is also called grad T. Some people write like this, or gradient of T. Gradient is some kind of slope. Okay. In this case, it's a 3D slope. 3D slope means in which direction you have to move so that the change is maximum. Okay, that is del T. We will use gradient of a scalar. We will use it in our course soon. You can apply del on a vector. You can take dot with some vector like velocity vector or force or whatever. If you do a dot, this is called divergence. Divergence. We don't use it much right now. Maybe second year a bit. What does divergence tell you? If a vector is diverging or not. If something is diverging like this, there is a huge divergence. For example, we'll see later in second year, if you have a positive charge, the electric field lines are diverging from it. Huge divergence is there here. Okay. What about suppose if there is a vector which is like this, then it turned like that, then from there it turned like this. It's not diverging in that sense. Okay, it's not diverging. Okay, if it is coming like this, there is a negative divergence or convergence basically. So if divergence is zero, the vector field is not diverging. The force field or velocity field or whatever. How to do divergence? See, del is I dou by dou x plus j dou by dou y plus k dou by dou z. And suppose my velocity is given as vxi plus vyj plus vzk. Then you take dot product, you will get dou vx by dou x. Ultimately, you are getting a scalar. Dou vy by dou y plus dou vz by dou z. This is called divergence. So when you take del and dot it with a vector, it's called divergence. When you apply del on a scalar, it's called gradient. Okay, it's called gradient. Del temperature, del energy, whatever. We will see later minus del potential energy. It gives you force, conservative force. We'll see all this soon. The third is you are doing this called curl. Curl. You are crossing the del with some vector. It's called curl. Curl of a force. This is what if it is zero, then I am saying the force is conservative. What is meant by curl? Suppose there is a field which is turning like this. There is a huge curl. It's curling like a whirlpool in a river or a sea or wherever. Whirlpool. That's there is a it's curling. So then curl is not zero. For example, if I have a vector field like this, it's diverging, but there is no curl. Curl means it should again come back like that. There must be some. It's turning backward. Okay. So if curl is zero, that force is conservative. That force is conservative. How to do curl? Same way as you do vector. You can remember it like this, but it's not a determinant. In determinant there is you can expand by any row, but this is not determinant. You have to expand only by top row here. You wrote ijk, you wrote dou by dou x, dou by y, dou by dou z, then force components fx, fy, fz. If you expand this, you get curl. Okay. If that is zero, then that force is conservative. So we have got three things. For example, if I take a force which is given by yzi plus zxj plus xyk, okay, is this force conservative or not? Let's check it. Let's do del cross f. Del cross f is given by ijk. Then first row you will write dou by dou x. It's not determinant in that sense. Determinants have got a property. You can expand them by any row, but this has to be expanded by first row only. Okay, because it contains a vector operator. That's the problem. Anyway, I into, if you close the row and column, dou by dou y of xy. Dou by dou y means only y is variable, x is a constant. X into dou y by dou y is 1. So x into 1, x minus dou by dou z of zx is x minus j into, close the row and column, dou by dou x of xy will be y. Dou by dou z of yz will also be y. Okay, so it will be y minus y plus k into z minus z. You are getting it as 0. So this is a conservative force. This force which you have here is a conservative force. So what are the definitions of conservative force? Let us once again go back and see what are the definitions of conservative force. We will see many more things in our next class. But if work done by a force in all closed paths, whichever closed path you take, if it is 0, then it is conservative force. Or curl is 0. Del cross f is 0. That's a conservative force. Or you can say work done is path independent also. Work done by a force is path independent. So next class we will build more on these ideas. Okay, many more things we will see. Very important chapter. It lays foundation for all future chapters also. Okay, so I think I'll close it here. Any doubts? Is it okay? I hope I made everything clear. Any doubts you have? Or is it too much? Yes, Hamna? Why not?
No, sir.
Okay, okay. Cool. I'll just send you this